Okay, now let's talk about a neuromodulatory effect called long-term potentiation, LTP. So, neuromodulators, such as dopamine, in this example, can contribute to the induction and maintenance of long-term potentiation, a persistent increase in synaptic strength associated with learning and memory. And so long-term potentiation is something, or modulatory effects that can whose effects are lasting, even over the course of a lifetime of an organism. So they're very long, potentially very long lasting. So let's take a look here with this example with dopamine and the modulation of synaptic plasticity. Okay, so in this example here, we're working with dopamine. So dopamine being released by our presynaptic neuron, binding to this metabotropic G protein coupled receptor, which is the D1 receptor, the dopamine 1 receptor. And it is involved in a signal cascade, secondary messengers, just like all the others. And so what binding to the dopamine 1 receptor involves is something called adenocyclase. And let me make sure that I've got that spelled right. Yeah. So adenocyclase, what this does is it breaks up ATP into two different parts. First, it gives us a diphosphate, and an AMP, and specifically cyclic AMP, right? A cyclic where we have before adenosine triphosphate, it gives us two phosphates, and a cyclic adenosine monophosphate. So adenosine with just one phosphate left onto it. And so what this does, well, first, what it'll do is it'll, our cyclic AMP specifically, oh my goodness, will act as a secondary messenger leading to signaling that will potentiate our NMDA receptors. And so what this will do is enhance the signaling, enhance the affinity for glutamate. Right, so this will become more sensitive to glutamate signaling. Right. So it will potentiate. So this is we're talking about a long-term potentiation here, right? And so here's a form of potentiation. But let's talk about what we came here for is the long-term potentiation. And so the cyclic AMP will also move further down and actually go all the way to the soma, to the nucleus. And what it will do is it'll induce through, again, I just want to reiterate the point that there's multiple steps going on here. It's not quite this simple. And so this will lead to an activation of transcription factors. And so this is the first example of our neuromodulation where we've seen actually inducing, affecting transcription. Right? And so what this will do is it will increase the transcription of the genes that will code for NMDA receptors. Right, and so this will produce our NMDA receptors. And they will be brought up to our membrane and incorporated. And so we've increased the density of our NMDA receptors, right? And these are, I don't want to remind you, right, that our MDA receptors, with glutamate are excitatory. Right? So if we go through and write, this will dramatically increase our NMDA receptors, right, potentially. And so the more receptors we have in the postsynaptic cell, plus with this extra potentiation in real time with dopamine 1, we are making this postsynaptic cell more sensitive to signals from the presynaptic cell, because there are more receptors here, so that it's going to be able to bind more glutamate. And the more glutamate channels that you can activate, the more positive ions that flow into it, the easier, the faster it'll be for it to depolarize. You don't need as strong of a signal to depolarize the cell to threshold to induce an action potential. And this increase, this uptick in transcription and migration of NMDA receptors to the membrane can be long-lasting, right? And this is one of the fundamental foundations of our modern theory of the neural basis for learning and memory, is this long-term potentiation. And so for those things that you've committed to long-term memory, whether it be 15 years ago or 2 months ago, is due to, in part, this long-term potentiation is due to the sheer fact of bringing more excitatory glutamate receptors to your postsynaptic neuron that are associated with that specific memory, that specific information. So pretty neat, huh?